So now I have to, okay, so in addition to that, I have to set my x0. Actually, I need to set my before the Newton's relation. I need to remember what my solution needs. So that then I have to passing my original x0 into both the residual and the Jacobian. Make sense? Because that's what I need to evaluate these derivative terms in the equation. I also need c by dc, right? So because here I'm dividing by delta c and I multiply by c here, right? So I also need to pass in that. I also need to pass in c and dc. So let's do that. And if you want to save some variable passing, you can just pass in the ratio of this. All right, which I am not doing here. So we have these additional variables that goes into g, that goes into ga, that goes into ga. It also goes into the Jacobian of ga, and also I need the Jacobian itself. So this and this. Okay, now the remaining task is to actually use this additional information in GA, in the governing equation, and then figure out the Jacobian of these additional terms in the Jacobian code, right? Does it make sense so far, what we are trying to do? Okay. David? Okay, good. So GA is equal to this. Now we have additional term. Memory. Okay. So what is this additional term? So first of all, we need to move this to the left hand side for Newton's method, right? So it has to be minus. So I would just say RHS is equal to let me just say memory is equal to U times du dc, right? U times du dc. Is it minus? Is plus actually. Is it plus? Did I actually mess up with the sign somewhere? Somehow I remember it was minus somewhere. It's yeah, it's minus. It's minus. So I did mess up with the sign. So this is minus. Okay. Minus down here, it's better. Okay, minus du d eta times f of eta. So du d eta, wait. So I actually called u to be fp, right? So dfp dc plus du d eta, which I called fpp, times df dc. All right. Minus. Thank you. And let's start calculating what these are. dfp dc is equal to fp minus fp0 divided by dc, right? And df dc is equal to f minus f0 divided by dc. Now we need f0 and fp0. But luckily we have x0, so let's just copy these lines and put it here. I don't need the fpp0, only need f0 and fp0, so let's add the zeros here. And now we have everything we need to compute the memory term, right? Okay. Questions? And my right hand side is going to be equal to we use the trapezoidal rule, memory 1 to n minus 1 plus memory 2 to n divided by 2. So that's my right hand side. And my gxa is equal to gxa minus right hand side. Alright, all done. That is going to give us an evolutionary boundary layer. But now, yeah.
When you bring in the previous solution at 0, are they stored at i's, not the endpoints? Which one are they saved?
Yeah, that's a good question. All the grid points, all the solutions are saved at the integer grid points.
Okay.
And we had a second order, so we have a mixed order discretization here. On the eta derivatives in the one normal direction, we use the all second order differential finite difference approximations. In the x direction, due to my laziness, I use the backward Euler as opposed to BDF2, right? So we only have a first order approximation in the x direction. That is why we are approximating the solution we are approximating the derivative at the integer points, but we are actually using a central difference at the half grid points, which corresponds to the backward difference at the integer grid points. So if this approximation is at half grid points in C, then it is second order. But using it at integer grid points on C, it is only first order. All right.
But in the y direction, you have second.
In the y direction, we have second order approximation to everything.
That's why we take line 21.
That's why we are taking line 21. Yeah, that's right. Because we are. If you don't use line 21, you're only biasing it. For example, if it's just the memory 1 to the n minus 1, then even your eta direction becomes first order. You're still going to get a convergent solution, but less quality. All right. Any other questions?